a quick recap of what we were doing in the last class. We saw that if you take an LPTV network N, which is LPTV at Fs, and you excite it say with a voltage Vi of t, and look at the output V out of t, and let us say we are only interested in samples. In output samples, V out of n comma Ts. So, the key points to note are the sampling rate is exactly the same as the rate at which the system is varying, right. Then we saw that you can think of V out of Ts as taking V I of t, processing it through a linear time invariant filter, right, with a transfer function H equivalent of j 2 pi f, and sampling its output at NTS, right, and H equivalent of j 2 pi f is nothing but the sum over all k of H sub k of j 2 pi f. That is all. It is simply the sum of the harmonic transfer functions, right. So, why is this a useful result? Well, useful because many practical situations arise where the output of an LPTV network is sampled, right, and we saw several cases yesterday. For example, we saw the sample and hold, we saw a switch capacitor circuit, we saw a continuous time delta sigma converter, right. And so, it is only the sampled output of the system which is of interest, right. And in such situations, it does not make sense to kind of work with the continuous time output, because the continuous time output has got a lot more information than the samples. If you are only interested in the samples, it may make sense to work with a time invariant system, where all calculations, convolution, everything, right, is much more easy to do. Okay. So, the summary is that this is a very useful result in practice, and many times, and because you have so many practical systems, many times you also have the situation where you have multiple inputs okay. So, you have V 1 of t, I 2 of t, blah blah blah, right, and this is a network N, and it is LPTV at Fs, all right, and the output is sampled at Fs, right. So, this is V out of NTS. all right. So, and many cases in a very practical situation that occurs is that when V1, I2 etcetera are all noise, right, because in a practical LPTV circuit it's very likely that you have multiple noise sources, right, and therefore, you would like and the output is a sampled output. So, you would like to find the transfer function from each of those continuous time noise sources to a sampled output, and I mean now that we know this principle of the equivalent transfer function, LTI transfer function, you basically for instance have say H equivalent 1 of t, which is the impulse response corresponding to H equivalent of j 1 of j 2 pi f. So, and this is V 1, you have H equivalent 2 of t I 2 blah 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 H equivalent L of t, and we have V slash I f. So, there are multiple input sources. You have multiple outputs, right. So, you sample this at Fs, and so V out of NTS is simply the sampled output of the sum of multiple linear filters being driven by different sources, right. Okay. So, the question now is, what is the question that we need to ask now? Well, the obvious question now is, how do we, well, this is fine to say from every input to the sampled output, you can think of it as the input driving an equivalent linear time invariant filter. The question is, how do we find H equivalent of t, right. We will assume, we will do this for one input, and then the same procedure will follow for all the inputs. Okay. So, remember, I mean, we can think of many ways of doing this, right. The first, so idea 1, let us say, is to say, well, we know that H equivalent of j 2 pi f is sum over k H sub k of j 2 pi f, right. So, this is basically suggesting, so find all H sub k of j 2 pi f, all right, and then find their sum. So, then add up all the H sub k's, all right. So, what comment can we make about, so what do we think, I mean, this is a smart way of doing this or a dumb way of doing this?
Like finding all H of k is like, again, we have to like a lengthy process of portion we have to apply.
Right.
We can use the reciprocity.
Yeah. So remember that to first find all the H sub k of j 2 pi f, so finding for all k is a time consuming process. So, in other words, you need to do a lot of hard work. right? And then of course, once you find them, adding them all up is, that's easy, right? But what comment can we make about the amount of information in the sum of h sub k, right, versus the information in the individual h sub k's all put together, which has got more information? Yeah. So, basically there is finding the individual harmonic transfer functions is a lot of work, and you do get a lot of information because you are getting each one of those functions individually, right. Then what are you doing? You are adding all of them, and the sum obviously has got lesser information than the individual parts, right. So, you are working so hard to get all this information and then throwing most of it away because you are only interested in the sum, right. So, this has got lesser information than the individual harmonic transfer functions, right. So, we have thrown a lot of information away. Right. So, clearly if we are only interested in the sum of the harmonic transfer functions, you know, it is evidently not a very useful thing to do, right. It is not a, you know, it is not a smart thing to do. Well, the next thing is to use something that we saw earlier with respect to reciprocity, right. Remember, and before that I would like to draw your attention to another way of doing this. So, remember that if we had the same input exciting both an LPTV system right and an equivalent LTI system, right. So, rather I would like to call this talk about this in the time domain H equivalent of t, and if we sample both these outputs, right. The idea is that, I mean, the fact that the lower arm is equivalent to the upper arm means that the two samples will be the same, right. Now, the question is, you know, what do we do about, how do we get this H equivalent of t? So, let us say we put in, let us say we excite the input with, let us say we are only interested in finding H equivalent of 0, right, just for argument's sake, right. So, if I am only interested in finding H equivalent of 0, what will I do? What do I mean, what can we do?
Time t.
Yeah, at time
T equal
0, what?
We will sample that.
We will sample, but what are you going to do with the input?
Input will be previous up to 0th instance only will be there.
Do you understand the question? The question is, if I am only interested in finding H equivalent of 0, that is the value of the impulse response H equivalent of t,
We will apply it to 0.
very good, right. So, basically if you are only interested in finding H equivalent of 0, you excite with delta of t, right, and what will you get here?
There H equivalent to 0 will
You will get H equivalent of t,
be of t, and we will sample.
right, and if you sample at 0, right, you get H equivalent of 0. Here is what you would have gotten if you knew the H equivalent of t, right, but the only access you have is, I mean, you only have the LPTV network, correct. and you are trying to find H equivalent of t. So, if you sample the output of the LPTV network at t equal to 0, right. So, what will you get? This must also be equal to H equivalent of 0, right. Measure at t equal to 0, all right. Now, if I want to find, so let me write this down properly. Right. So, if you want to find H equivalent of 0, you excite the LPTV network with an impulse at t equal to 0 and you measure at t equal to 0, correct. Now, if you want to find, let us say, H equivalent of delta t, where delta t is some small positive time, what do you think you will do?
We'll measure at the
Remember, this is only, I mean, we are sampling only at
TS.
multiples of Ts, right, but we want H equivalent of delta t, where delta t is smaller than Ts. What do you think we can do? We can't change the sampling instants because you are only sampling at
TS
multiples of Ts. So, you can't say, I mean, you can't say you put delta of t and you measure at delta t. What else can you do?
we can shift the impulse by delta t
To the left or right?
to the like positive time we can like
You can only sample at 0 or Ts or 2Ts or and so on, correct. If you shift the impulse to the right,
and t plus delta ts we have to sample like
t not even t plus delta Ts, right. So, now think and tell me clearly at what should you do to the input impulse, so that when you sample at t equal to 0, you will get H equivalent of delta t.
t plus delta t we have to
So, you have to apply an impulse at,
t plus delta t.
so you excite with delta of t plus delta t. In other words, you are applying an impulse at delta t before. So, if you apply, this is 0 and you apply an impulse at minus delta t, then what do you get?
Here H equivalent of t
You will
plus
get,
delta t
you will get H equivalent of t
plus
plus delta t. When you sample it at 0, what will you get?
H equivalent of delta t.
Yeah. So, you will measure at t equal to 0. Does it make sense? All right. Now, if you want, so delta t can be,
Less than
if you want the impulse response at any amount of time, right, for any time delta t, this is valid for any delta t, correct. So, if you want, for instance, H equivalent of Ts, what will you do? You will apply the input impulse at,
ts before the
yeah, Ts before 0 is what time?
h of minus ts. Delta of t plus ts
Which is, therefore, you apply the impulse at
minus ts.
minus Ts, right. If you want if you want to find the impulse response H equivalent of t at a particular time, say Ts, then you will apply the input impulse at minus Ts and sample the output at 0. Does it make sense? Right. So, right. So, therefore, for any delta t, right, apply impulse at minus delta t. So, that is that which basically means that you have delta t, the Dirac impulse is applied at delta of t plus delta t, and sample or measure the output of the LPTV system at t equal to 0. All right. Okay. So, if you want to find the H equivalent of t for all time, what will you do?
We'll apply impulse.
You apply an impulse at 0, measure the output at 0, apply an impulse, run a second experiment where you apply an impulse at minus delta t, where delta t is a very small increment in time. You measure the output at 0, then you do 2 delta t, right,
Like that we
and so on. So, experiment therefore to find H equivalent of t, right, excite the LPTV system at 0, measure output at at 0, excite experiment 1, then experiment 2 is excite
LPTV system at
the LPTV system at,
minus delta
when I say excite, it means that
impulse.
all you apply Dirac impulses, right, at minus delta t, measure output at 0, right. Experiment 3, excite the LPTV system at minus 2 delta t, measure output at 0, and so on and so on and so on until do infinite number of experiments, so that you will be able to get the response for all t, right. As delta, I mean, if you want, as delta t tends to 0, you will basically get,
Like all the
you will be able to get all the values, right. Now, what is the problem with this? The principle is okay. What is the problem?
practically it's not.
Well, you have to run many experiments, right, and but what do you notice? In all the cases,
Output
the exciting input is being changed, right, but the output is always being measured at the
0.
same time, right. So, this basically now should ring a bell, and now we should be able to exploit. Remember, whenever the you have multiple, you do an experiment with multiple inputs and you have the same output, it always makes sense to exploit reciprocity, and that is not what we are going to do next. And the key point is to notice that our output measurement always occurs at t equal to 0. All right. So we now exploit or recall that if you have an LPTV network at Fs, which is LPTV at Fs, you apply say whether this is a voltage or a current source, it does not matter. If you apply an impulse at T1 and measure at VO of T2, another, if you take the adjoint network and excite it
minus t plus t1 delta of t
delta of excite the output port at
t plus t2 like minus t2
we excite at t plus t2 and measure VO hat of
t1
minus T1, and it turns out these two will be the same, right. So, this is the adjoint. All right. Okay. Now what do we how do we apply this principle? Well, experiment 1, we excite the LPTV system at 0, you measure the output at 0. So, you will get the same output if you take the so in our experiment. So, experiment 1, which is this fellow here, right. We will take the adjoint network, this is the adjoint, right. We excite the output port with
impulse at 0
at 0, because we are measuring, we are exciting at 0, we are measuring at 0. So, if you take that joint, you inject an output impulse at 0 and VO hat.
of 0
So, VO hat of 0 must be equal to. So, V out of 0 that you measure is basically H equivalent of 0. Does this make sense? All right. Now, what about experiment 2?
we will apply the impulse at t plus delta t.
You must apply the
Sorry,
in the original experiment, you apply if you had to do it with n, you would apply an impulse at minus delta t and measure the output at 0. So, in the adjoint network, what should you do?
we have to apply the impulse at 0 at output port and measure the output at the input port at delta t.
Exactly, right. So, I mean, but applying the impulse at 0 at the output port, we have already done, correct. Okay. So, if you simply measure VO hat at delta t, what will you get therefore?
That H equivalent of delta.
You will get H equivalent of delta t. Does it make sense? Right. And similarly, VO hat of 2 delta t is basically H equivalent of 2 delta t and so on, correct. So, what is the moral of the story? What is the waveform? So, if you excite the adjoint network with delta of t, what is the waveform that you will see here?
That is H equivalent of
You will see H equivalent of t. Does it make sense, right? So, as we have seen with in earlier cases, the adjoint is a great way of simplifying the analysis, or reducing many experiments into one. So, this is the bottom line, therefore, is that you form to find H equivalent of t, right. You form the adjoint n hat, all right. You excite the output port with
impulse at t equals 0.
delta t, right, and port with delta t, correct, and just simply, so H equivalent of t is the waveform developed at the input. Right. So, H equivalent of t is what is developed here, right, and this was when this situation corresponds to actually in our original network we had a voltage input. Let's I think I should make it, I'll just make it current input, that's easier, right. So, this is actually a current source and the output is the output of the transfer function is of interest is you excite it with the current, you measure the voltage, correct. So, in the adjoint you excite the output port with a current and measure the voltage developed at the input port. Now, of course, the other corollaries are pretty straightforward. This is if the network is being driven by a voltage source and the output is a voltage source, then to find H equivalent of t, what should you do? Well, you find that joint. So, this is 1, and this is 2 prime, and you excite the output port with a current impulse at t equal to 0 and measure the current in the input port. So, this current here will be proportional to H equivalent of t. Remember that the H equivalent of t in this case, where you have a voltage input, voltage output, physical dimensions are what are the physical dimensions? We have discussed this already in connection with impulse response long ago. The physical dimensions of H equivalent of t is 1 by second, right, but this is actually a current which is being developed, right. So, you have to divide this by ampere second. So, this is if delta of t, this is an input current. So, this the dimensions of this are basically the physical dimensions of this are amperes, correct. So, if you have a wire and you are measuring current, you will measure amperes, correct, but impulse response has got dimensions of 1 by second. So, to get the so let me kind of be a little more careful here. So, this is I out, right, whose physical dimensions are amperes. So, to get from I out to H equivalent of t, what should you do? I out divided by amperes times second is H equivalent of t. Does it make sense? So, the output current waveform has the same shape as the impulse response, but only the y axis has got one is hertz, I mean per second is hertz, right, and I out is amperes. So, you just have to divide by ampere second, which is basically a coulomb, right. So, this is the same thing that we saw in connection with impulse response when we did noise in linear time invariant networks. Okay. And likewise, if you have a current input and a voltage output, I mean we have already seen current input, voltage output, voltage input, voltage output, current input, current output, then the adjoint will be a voltage input and voltage output. And similarly, if you have a voltage input, current output, then you have a current input, voltage output, right. I mean I think this is the very simple, right.